Good morning, dear student. In previous lecture, we already discussed the mechanism of substitution, that is SN1 or SN2, and second, that is the kinetics for this SN1, SN2, and interchange mechanism. So, in today's lecture, we are very much interested in the important points regarding to this substitution reaction, that is experimental evidences in octahedral substitutions. So, how this reaction undergo either dissociative type of mechanism or associative type of mechanism. So, these are the some evidences for this octahedral substitution reaction. The first one is your dissociation. We know that is whatever the substitution reaction in these coordination complexes, they uh, they undergo through dissociative type of mechanism. So most of the reaction undergo dissociative, it will shows dissociative type of mechanism for substitution reaction. Okay, so these are the evidences. First one is the dissociation, second the linear free energy change. Okay, we can consider it is as activation energy. Third one is associative mechanism. So we are not very much interested in the associative mechanism, because whatever the substitution reaction of this coordination complex, they follow the SN1 mechanism, that is dissociative type of mechanism. The fourth one is conjugate based mechanism. Okay, so what is this conjugate mechanism? Conjugate based mechanism we will discuss this reaction. And the last one is kinetic Chillet effect. So these are the five evidences in octahedral substitution reaction. Out of that, the dissociation conjugate based mechanism is very important, and the kinetic Chillet effect is also important. Associative type of mechanism, we are not very much interested in the associative mechanism, because whatever the reaction, the substitution reaction mostly occur through dissociative type of mechanism. So let's discuss one by one uh, evidences for this octahedral substitution. The first one, that is your dissociation. Okay, so we are very much interested in the first one, that is your dissociation. So we are very much familiar with this dissociative type of mechanism. Let us discuss some important points regarding to this dissociation. The first important point, that is the evidences for this dissociative type of mechanism. The first one is that the rate of reaction. So we are very much familiar that in dissociative type of mechanism, the rate is directly proportional to the concentration of the reactant, means the concentration of coordinated complex, metal complex. So the first evidence is for this dissociative type of mechanism, that the rate of reaction, the rate of reaction changes, the rate of reaction changes only slightly, only slightly, the rate of reaction changes only slightly with changes, changes in the incoming ligand, with changes in the incoming ligand. For example, if you consider the example of this point, so this is the first evidence for dissociative type of mechanism, that the rate of reaction changes only slightly. So the rate of reaction is comparable with the incoming ligands. Either it is if you consider the incoming ligand is different, but the rate of reaction is similar to all these ligands, that is the rate of reaction changes only slightly with change in incoming ligand. For example, the equation reaction, the equation reaction. So we are very much familiar. Equation means what? The substitution by the water molecule or water as a ligand. Equation reaction, substitution by water. And second, that is the annihilation reaction. Annihilation reaction means substitution by anion, substitution by negatively charged ligand. substitution by anion. So this is the important points or important evidence for this dissociative type of mechanism, that the rate of reaction changes only slightly with changes in the incoming ligand. The example is aquation reaction, and second is annihilation reaction. Annihilation reaction, because we know that in dissociative type of mechanism, uh, a dissociation of the ligand, a dissociation of one of the ligand from this metal complex is the rate determining step, and the entering group should have no effect on the reaction rate. That is, whatever the incoming nucleophile, it does not affect on this rate of the reaction, and therefore the rate of reaction changes only slightly with change in the incoming ligand. For example, the aquation and annihilation reaction. If you consider the reaction, that is, for example, we consider the aquation reaction, that is CO NH35 CO NH35 Cl, it is in plus 2, it having plus 2 charge, and when water has an incoming ligand, then we get this, that is CO NH35 H2O, and it having cobalt, it is in plus 2 oxidation state. Okay, so this is your aquation reaction. So instead of if you consider, instead of other ligands, okay, this is your first example, that is aquation reaction, and another is annihilation reaction. Okay, so this is your aquation reaction, and if you consider the second, that is annihilation reaction. Annihilation reaction means what? We could take same complex, and that is NH35. Here we take water, H2O, okay, and this is in plus 3 oxidation state, this cobalt in plus 3 oxidation state, and the incoming ligand, if it is water, okay, so the incoming ligand may be your water, then it may be your N3 minus, okay, then it may be your SO4, we can write. The incoming nucleophile may be your water, maybe your N3 minus, maybe your sulfate SO4 2 minus, maybe your chloride Cl minus. So this is your annihilation reaction, means substitution of one water molecule, or one substitution of water ligand by the another anionic ligand. So in this case water is also there. Okay, so these are the negatively charged species. N3 minus is there, sulfate is there, chloride is there, then NCS is there. Okay, NCS minus is there, and if you find out the rate for this reaction, then the rate is not different, because for water and N3 minus the rate constant is 100. So it is a first order reaction, so we can consider it is K1, it is 100, okay, 100 per second. Okay, so when the ligand is water, incoming nucleophile is water or N3 minus, the rate is same. Again, if you consider the sulfate and this chloride, then the rate is 24 21 per second, 21 24 24 21 per second, means the rate is not different, the rate is slightly different. Okay, it is comparable, so we can consider it is one and same. Okay? So there is a no change, the rate of reaction changes only slightly with change in incoming ligand. Similarly for this NCS minus, it is 16 per second. So these are comparable value, so they are not slightly different. So this is the first evidence that the rate of reaction changes only slightly with changes in incoming ligand, because we know that in dissociative type of mechanism, the rate of the reaction is totally depend on the concentration of the coordinated complex. It is not depend on the incoming ligand, and therefore if you vary this incoming ligand or incoming nucleophile, then the rate of the reaction is comparable. So it will show slightly change. Okay, the rate of reaction is slightly changed with incoming ligand. So this is the first evidence. So you should keep in mind the reaction, that is annihilation reaction, substitution by water molecule. Okay, substitution of one or more water molecule by anion. Okay, it is called annihilation reaction. So this is the first evidence. Let us consider the second important points regarding to this dissociative type of mechanism, or the evidences for dissociation. That is, the second point is very important: decreasing negative charge, decreasing negative charge decreasing negative charge, or decreasing negative charge on increasing positive charge, or increasing positive charge on the reactant, on the reactant on the reactant on the reactant complex. Okay, so decreasing the negative charge or increasing the positive charge on the reactant complex, the rate of reaction the rate of reaction or the rate of substitution, we can say that the rate of substitution is decreases. The rate of substitution is decreases. So this is also the important evidence for dissociative type of mechanism. So already we discussed the first one, that is the effect of incoming nucleophile or incoming ligands. Okay, so the rates are comparable. The second point is very important, that is decreasing the negative charge. Okay, so the negative charge is decreases on the complex, reactant complex, or increasing the positive charge on the reactant complex, then the rate of substitution reaction is decreases. Or we can say that the whatever the reaction which undergo dissociative type of mechanism, the rate of this substitution, that is dissociative type of mechanism. Okay, so rate of this substitution is decreases with decreasing the negative charge or increasing the positive charge. Okay, so let us discuss the example, that is if you consider the oxidation state of central metal atom. Okay, and if you consider the charge on this complex. Okay, so let us consider that is this complex, that is Al F6 3 minus ion is there, Al F6 3 minus ion is there, then Si F6 2 minus ion is there, and then Pf6 having negative charge, and then finally the SF6. So what this point indicate, decreasing the negative charge or increasing the positive charge. So if you consider this is the species, that is it having -3 charge on this complex, it having -2, it having minus, and it have a neutral species. Okay, so decreasing the negative charge or increasing the positive charge. So negative charge will be decreases, means we can consider the oxidation state of this metal atom is also increases. Okay, so negative charge is decreases, means what, the oxidation state of this metal atom is increases. So in this case, this aluminum, it is in +3 oxidation state. In this case, this silica, it is in +4 oxidation state. Then if you consider this phosphorus, it is +5 oxidation state, and this sulfur, it is in +6 oxidation state. That is, the oxidation state of central metal atom is increases. Okay, higher the oxidation state of this central metal atom, slower the ligand exchange rate or slower the rate of the reaction. So this is the point, that is decreasing the negative charge or increasing the positive charge on the reactant complex. Okay, So in this case we consider only the negative charge and the oxidation state of this metal atom. Okay, so you should keep in mind, decreasing the negative charge or increasing the positive charge on the reactant complex, the rate of substitution reaction is decreases. So this is also the important evidence. So in this case, this complex will have a maximum rate of ligand substitution. So the rate of substitution is follows in this order. So if you consider the first complex, it will have a maximum rate of ligand substitution as compared to this SF6, because we know that decreasing the negative charge, so in this case the negative charge is decreases, and therefore the rate of ligand substitution is decreases. The rate of ligand substitution is decreases. In other word, we can say that increasing the oxidation state of metal atom, increasing the oxidation state, so oxidation state of metal atom is increases, oxidation state of metal atom is increases, the rate of reaction or rate of substitution, the rate of substitution is decreases. So you should keep in mind that decreasing the negative charge or increasing the positive charge. So we consider the example in which the negative charge decreases, and also we find out the oxidation state, that is decreasing the negative charge or increasing the positive charge on the reactant complex, then the rate of substitution reaction is decreases. In other word, we consider the oxidation state, that is the oxidation state of metal atom is increases in the reactant complex, then the rate of substitution reaction is decreases. Let us consider the second, that is increasing the positive charge. Let us consider this example, that is we considering these complexes, that is NiH2O n number of times having +1 charge. Okay, then Mg H2O, okay, it is in +2 oxidation state, it is having n number of times, and then Al. Okay, so we can consider it is 6, coordination number is 6 for same, coordination number is 6 for all these metal complexes. Okay, this sodium complex, magnesium complex, and aluminum complex. So if you consider here the +1 charge is there on this complex, here the +2, and there is +3. So we know that decreasing the negative charge, we already discussed the example, or increasing the positive charge. So as the positive charge on the complex is increases, on the reactant complex is increases, the rate of ligand substitution reaction is decreases. So in this case also, this complex is have a higher ligand substitution reaction, higher rate of substitution as compared to these two complexes, and the third complex will have lower, okay, or slower exchange rate ligand substitution, slower exchange rate ligand substitution reaction, slower exchange rate, because we know that as the positive charge on the reactant complex is increases, the rate of ligand substitution reaction is decreases. So this is the second evidence for this dissociative type of mechanism. The first one, that we know that in dissociative type of mechanism, a rate is directly proportional to the concentration of reactant only. Okay, it is not depend on incoming nucleophile, and therefore if you vary the incoming nucleophile, then the rate of reaction is comparable, okay, with different ligands, with different nucleophiles. In the second point, that is decreasing the negative charge or increasing the positive charge on the reactant complex, the rate of substitution reaction is decreases. As the oxidation state of metal atom is increases, the rate of ligand substitution reaction is also decreases. Okay, and another point is also important in this second point is that smaller the ions having slower exchange rate. So you should keep in mind, smaller ions means whose ionic radius is very small, smaller ions means they're having large charge. So we are very familiar. So when the ions is smaller, so it having a maximum positive charge. So smaller ions have slower exchange rate, slower exchange rate or ligand substitution rate, slower exchange rate. Smaller ions having lower exchange rate. For example, if you consider this complex, that is strontium complex, it is all these metal atom, all these atom having same oxidation state, that is CaH2O6, it is in +2, and the third one, that is MgH2O6, it is also in +2. So in this case the oxidation state on this complex is same. So a decreasing negative charge or increasing positive charge, this factor it is not applicable here. Okay, so we know that the oxidation state of metal atom is increases, the rate of ligand substitution reaction is decreases. But in this case all these metal atoms in same oxidation state, that is in +2 +2 +2. But the important point is that smaller the ions have slower exchange rate, and we are very much familiar with this uh, ionic radius. So if you go from top to the bottom in periodic table, the ionic radius is increases, and if you find out the ionic radius for these complexes or this metal atom, then it is 112 picometer, then it is 99 picometer, and this is 66 picometer, double 6 picometer is there. So what is the point? That is smaller the ions have slower exchange rate, smaller the ions. So those having smaller ionic radius is very small, they're having lower exchange rate, or lower they will the rate of the ligand substitution is very slow or very low in these complexes, because they're having is small ionic radius, means they're having a larger charge. Okay, so they're having more charge. Okay, so the nucleus exerts more charge on this, we can consider the nucleus exert more charge on these ligands. Okay, so metal atom, so there is a strong interaction between this metal atom and the ligand, because it is small size, so small size and the ligands. Okay, so there is a strong interaction, and therefore the rate of ligand substitution is very less in this magnesium complex as compared to this calcium strontium complex. So the rate is like this. Okay, so this strontium complex having maximum rate of substitution as compared to calcium and magnesium. So smaller the ions or smaller the ionic radius, lower the exchange rate. Smaller the ions means smaller ionic radius. As ionic radius is decreases, a rate of reaction is also decreases, a rate of ligand substitution reaction is also decreases. So in already we discussed, as the oxidation state of metal atom is increases, the oxidation state increases means the ionic radius is decreases, so you should keep in mind that as the oxidation state is increases, the ionic radius is decreases, and as the ionic radius is decreases, the rate of ligand substitution reaction is also decreases. So this is the second evidence for this dissociative type of mechanism. Okay, so let us discuss the third important point, is that the steric crowding on the reactant complex, steric crowding on the reactant complex, steric crowding on the reactant complex increases the ligand, increases the rate of ligand dissociation. Okay, so this is the important evidence that whenever there is a steric crowding, whenever there is a bulky ligand is attached to the metal atom and the reactant side, in that case this steric crowding on the reactant complex increases the rate of ligand dissociation. Okay, when the ligands on the reactants are crowded, the loss of one of the ligand is made easier. Okay, so as crowding increases, as crowding increases, the rate of ligand dissociation. After dissociation, then there is a substitution. Okay, so the first step is dissociation. Therefore we consider, so as crowding increases, the rate of ligand dissociation is increases, or we can consider the rate of the reaction is also increases. Okay, so this is all about the dissociation. One or more important point is that this the rate of reaction is related to the linear free energy relationship, so we consider it is a separate point, and another is activation energy. Okay, so this point we consider in the second point, that is linear free energy relationship. For it is one of the evidence for this dissociative type of mechanism. So at least you should understand what is the dissociative type of mechanism, there is kinetics, and what are the evidences. So at least you should remember this important point, that is the effect of incoming ligands. Second, the effect of charge, that is negative charge or positive charge. Okay, and the third one is steric crowding. Okay, the steric crowding. Remaining 2 points we discuss in the second evidence, that is linear free energy relationship. Thank you.